In the previous video we looked at a couple of different overarching types of energy. In this video we're going to look specifically at one of those types being kinetic energy. As we saw in class, there are different forms of kinetic energy. Here we're going to specifically talk about kinetic energy as being the energy of motion of a mass, and we'll have a look at how we can figure out how much kinetic energy there is in an object that's moving. Now I need to mention here as well that one of the things that I think is important with physics is to understand where equations come from. So not just sort of be dumped with an equation, but to actually understand how the equation comes about and what its significance is. And so in this video I'm going to show you a derivation that gives us the equation for the kinetic energy of a moving mass. You don't need to know the derivation itself. I'm only including it to show you where the equation comes from. Now you can see here I'm sketching a bit of a scenario of where an object might be moved along a surface. We're going to imagine that that surface is frictionless, so that there's no effect of friction pushing back here, so the applied force is the only thing we need to look at. You can see there that we start off with an object that's stationary, we apply a force to it, it accelerates to some new position at some later point in time over here t, and at that point it has a velocity v, where initially the velocity was u, being 0. Now if we assume that a constant force is applied in this scenario, so that basically means that it just simplifies the situation, and you'll notice as we go through physics we're all about trying to simplify it so that we can then make sense of the basics and then introduce the complexity later. So if we have a constant force, that means we can use Newton's second law. And we know from Newton's second law that F is equal to ma, but we know from our equations of motion that acceleration is the rate of change of velocity, so we can call that v minus u over t. But in this case we know that u is equal to 0, so then the equation for the force then becomes mv over t. So there's the first simplification that we need to do. If we think about the distance, or the displacement I should say, at time t, we can use equations of motion for that. And hopefully you can see here the reason why we're doing this. We've figured out another expression for force, we're now looking at another expression for displacement, so we can figure out what the work is that's done by multiplying these two together. So first of all we've got s equals ut plus half a t squared. We again can identify that u is equal to 0, so this first term here will go to 0, so it disappears. So that leaves us with a half, and again we're going to write v minus u on t, and that's all going to be multiplied by t squared. Again, u being equal to 0 means that this term disappears. That leaves us with v on t multiplied by t squared, and so we end up with half vt. So there's our two expressions now for displacement and distance, and so the work done in time t to accelerate the box to that speed v, or that velocity v, means that we can then just calculate work being equal to force times displacement, and so that then gives us the expression for work was mass times velocity over time, and the expression for displacement was half v multiplied by t. Now if we extend that out, expand the brackets, we get an expression half m v squared. The reason for that, the t divided by t, they'll cancel, and so all we're left with is half m v times v, so half mv squared. So that's the work that's done in causing the box to accelerate to that speed v. So since the work done is going to be the same as the energy gained, that means in this scenario that the energy gained by the object that means then that we've got an expression there for the kinetic energy. So the kinetic energy of the box at time t is given by this expression, E. We're going to use a subscript k there to show that it's kinetic energy. So kinetic energy of the object is going to be half mv squared. That's another one that's in the data booklet. You'll notice there I've got representing it as a vector. We're really only interested in the speed, so we could just drop that the vector notation there and just look at the speed of the object. Now you might sort of say, well, hang on, that was with an initial velocity of 0. What would happen if we didn't have an initial velocity of 0? In that case, you'd actually have some kinetic energy of the box to begin with, and so as you accelerate it, you do more work on it, and so it's going to increase the kinetic energy. So it doesn't matter what your starting velocity is. Once you've got an object that's moving at a specific speed, you can use this equation to figure out what the kinetic energy is.